So let us start our discussion. So in the last class, we were talking about our decision tree concept. So let us try to apply that concept. So what is the first step that we are going to see? Import our libraries, pandas, matplotlib.library. Import your numpy library. And from ExcelR.model_selection import, train_test_split, because we are going to partition our data. And then from ExcelR.tree, import our decision tree classifier. So this is the function what we are going to use, decision tree classifier. And from ExcelR import tree, we are going to import our tree function for visualizing, creating our decision tree. That is the purpose why we are importing tree function. And from ExcelR.metrics, import classification_report if you want to find out your F1 score, accuracy, and other metrics for your decision tree model. And from ExcelR, import pre-processing. So this is what we are going to require for pre-processing our data. So we are going to work out on a simple data set here, iris data set. So it is a very popular data set that we are going to work with, iris. So here we have our different features in our data set. We have sepal length, sepal width, petal length, and petal width. So all these different features are measured in centimeters for us. Now, based on these features, we should be in a position to classify our species as Setosa, versicolor, and virginica. So let us try to classify our observations into three different categories: Setosa, versicolor, and virginica for us. Now, we are going to label encode. We are going to convert our categorical data into numerical columns. You can do this with the help of our label encoder. So transform your data, transform your categorical data into your numerical values. So apply your label encoder on your species column. That is what we are going to do. And then divide your data set into X and Y. So X is going to have my all the features, and Y is going to have my target variable. X is going to have my 4 features. Y is going to have my target variable first. So this is my X data, my input data. This is my X input data first. Now, this is my Y. I've converted my Y data. This is my target data. I've converted this data into our numerical values. Is 0, 1, and 2. That is what we have done. So you can scroll down. 0 stands for Setosa, 1 stands for versicolor, and 2 stands for our virginica. So we have our values. And this data set is having 50 observations for us. For every category, we have 50 observations. Total 150 observations we have. So it is a small data set that we are working with. Now, what are the different columns that you have? Sepal length, sepal width, petal length, petal width, and species. Now, before building your model, let us try to partition our data into training and testing. So we can use our train_test_split function and split our data. And we are giving 20% as the testing size for our problem. So 80% of your data will be used for building your model or for training our model. Remaining 20% of our data will be used for testing our model. So that is what we are doing. Now, let us build our decision tree classifier. And you can say decision tree classifier and criteria is equal to entropy. That is what we have seen yesterday. So you are trying to apply your C 5.0 algorithm on our iris data set. And we can mention some depth value to control your size of your decision tree. And you can fit your decision tree model on your training data set. So our model is developed now. It is a simple model what we have developed. We are fitting it on our training data set. Now, you can simply plot your decision tree. So tree.plot_tree, this function you can use and plot your decision tree model, what you have developed. Now let us try to slightly improve the quality of our decision tree. This decision tree is very small for us. So what we are going to do, we are slightly going to improve the quality of your decision tree. So I'm going to mention my feature names in my decision tree. I'm going to mention my class names in my decision tree. So I'm going to create a subplot with one row with one column, and I'm mentioning figure size and dots per inch. If I increase this value, I'll be able to increase the quality of my visualization. And then use the same function. Plot your decision tree on the model what you have developed and include my feature names and class names. And fill is equal to true means it is going to color your decision tree. So this is what we have. So what is our root node? What our model has identified? Petal length. Petal length is the most important feature in our data set. And this is the entropy value. So 120 observations are being used for training our model. So this is how we are constructing our decision tree. So this is our decision tree that we have. And then let us try to find out what are our important features. Our important features are petal length and petal width. So petal length is the most important feature for us, followed by petal width. And this is the information present in petal length and petal width. So these are my two most important features in my data set. So petal length is the most important feature. It will be considered as my root node. Now you can also plot it using your Seaborn library. You can simply plot it. So petal length is your most important feature. This is what we can understand. Now, predict using the model what you have developed. Model.predict on your testing data set. These are your predictions. And then you can use your crosstab function and you can find out your accuracy. So this crosstab function is very similar like my confusion matrix. And then I can find out the accuracy for the model what we have developed. So these are simple steps what we are writing down for building our model and finding out our accuracy. Now we can do the same thing with our CART model. All we have to do is change our criteria to Gini and then again fit your model. This is the CART decision tree classifier, what we are fitting on our data set, and make your predictions. Predict on your testing data set and find out what is the accuracy. Compare your predicted values and your actual values. So this is what we are going to do for your CART algorithm. Criteria is equal to Gini. Now you can also apply your decision tree regressor example. So from ExcelR.tree, import your decision tree regressor. This is the function what we are going to use. And now for the sake of this example, you can consider your petal width as your target variable. And all the other variables are going to be considered as your independent variables. So split your data and then fit your model on your X and Y training data. And then find out what is the accuracy on your testing data. So this is the accuracy what we are getting, 85.7%. So this is how we can build our decision tree models, our C5.0 CART models, and also our decision tree regressor models. So all these things we can build. So what is the next topic? What we are going to see today is our ensemble models. That is the next concept what we are going to discuss. Ensemble models. So what do you mean by ensemble? Ensemble means it is a collection, or you can call it as a mixture. So it is a collection or a mixture. So we are going to talk about a collection of models. So we're going to discuss the different ensemble techniques what we have. So broadly, we are going to talk about 3 topics. First, we are going to talk about bagging ensemble technique. And we are going to discuss the example of our random forest, which is based on the bagging ensemble concept. And then we are going to talk about our boosting. And we are going to talk about one of the boosting methods, add a boost. And then stacking. We can discuss the example of voting ensemble model here. So all these things we are going to discuss. So ensemble means it is a collection of models. It can be simply collection of decision trees for us. So what is the purpose of applying the concept of ensemble techniques? Why do I have to create my ensemble models? What is the logic? Ensemble models are going to improve the robustness, the reliability of our machine learning model. They increase the reliability of our machine learning model, and also they help us enhance the accuracy of our machine learning model. So that is the reason why we are going to apply our ensemble models on our data sets, and we'll try to see what kind of results it is going to give us. So what are the 3 ensemble techniques? You have your bagging ensemble model, you have your boosting ensemble model, and also stacking ensemble model. These 3 things we are going to discuss. Let us see one by one. So what is our bagging ensemble model? Bagging ensemble model, it often considers homogeneous weak learners. So if this is your data set, so if this is my data set, now I'm going to build my machine learning models on this data set, and then each machine learning model is going to make a prediction. And now my job is to consolidate all the predictions, to combine all the predictions what I'm getting from each and every machine learning model. And I have to make the final prediction on my data set. So bagging is a concept which is going to consider homogeneous weak learners. So all these machine learning models are homogeneous. So they can be your CART algorithm, for instance. So all machine learning models are going to be my CART decision tree models. I'm going to use them on my data set. And then I'm going to build my models and make my predictions. So every machine learning model is going to come up with a prediction. Now you have to consolidate all these predictions. You have to combine all these predictions. You have to combine all the predictions. And then you have to decide what is your final prediction using this bagging ensemble technique. So how can you combine these? A simple example can be, take the simple average of predictions what you are getting from different machine learning models. And this is going to be your final prediction. So that is how you are going to combine. So this is our first ensemble model. It is called as bagging for us. Now, what is the second ensemble model that we are discussing? It is called as boosting. What is boosting going to do for us? Boosting often considers homogeneous weak learners. So boosting also considers homogeneous weak learners for us. So you have a machine learning model. Now this machine learning model is going to make some predictions. So it has made some predictions for us. Now, the second machine learning model is going to work on whatever misclassifications were done by your first machine learning model. So it is going to try and correct and rectify all the misclassifications what your machine learning model 1 has done for you. Similarly, machine learning model 3, what is it going to do? It is going to try and rectify all the misclassifications what your machine learning model 2 has done. And then it will try to improve the performance of your model. Similarly, machine learning model 4 is going to try and work on all the misclassifications what your machine learning model 3 has done, and it will try and improve the performance of your model. So in boosting, all your machine learning models are sequentially connected. And you're going to combine all these models in a sequence. And you are going to build your ensemble technique. So this is called as boosting for us. So this is another ensemble technique what we are going to discuss. It is called as boosting. Then, what is stacking? Stacking is nothing but stacking considers heterogeneous weak learners. So stacking is going to consider heterogeneous weak learners. So my first machine learning model can be logistic regression. My second machine learning model can be support vector machines. My third machine learning model can be decision trees. So these are heterogeneous models. So these models I'm going to build on my data set, and I'm going to make my predictions using these models. And then my job is to consolidate all these predictions and then make my final prediction. So this is how your stacking ensemble technique is going to work. Stacking ensemble technique for us. So stacking works with heterogeneous weak learners. So we are going to apply all these concepts in our Jupyter notebooks, and then we'll try to see what kind of results we are going to get. So we are going to discuss all these concepts in few minutes. What is bagging, what is boosting, what is stacking. So this is the overview of our ensemble models. This is the overview. What we have to understand. Now, what is the concept of this ensemble? Suppose you are a contestant on a television trivia show. Suppose there is a quiz competition and you are participating in that quiz competition. And you had to answer this final question, which is going to give you $1 million prize. So there is one last question what you have to answer. If you answer that question, you'll end up winning $1 million. So what is that you're allowed to do? To answer that question, you are allowed to select a panel of 5 friends who are going to help you in answering the question. So they've given you this option of selecting a panel of 5 friends who are going to help you answer the final question. So what are you going to do? You are going to stack the panel with diverse subject matter experts. So you're going to call up all your friends and you're going to stack that panel with diverse subject matter experts. So you'll maybe talk to your friend who's coming from a literature background. You'll maybe talk to a friend who's coming from a science background, from history background, from art and pop culture. So all these are just examples for us. So these are the friends who you have, whom you are going to contact, and you are going to create a panel of with these backgrounds. So one friend is coming from literature, one friend is coming from history, one friend is coming from art, one friend is coming from pop culture. So this is a well-rounded group for us. So it is a well-diversified group for us. So now, given their breadth of the knowledge, it is very easy for you to answer the final question. So that is the advantage what you're trying to take by calling all your friends who are subject matter experts coming from different backgrounds, and they will help you answer the final question. So this is what we are actually doing in our Ensemble model also. This is what we are actually doing. So you have your training data, and then this data is going to be allocated to your machine learning models. So these are your friends. These are like your subject matter experts. So your friends are going to take a look at the question that you have, and they are going to help you answer the question. They'll give you all their opinions, what can be the possibility for the answer. And now what you're going to do, you're going to take all their opinions. You're going to take all their answers and you're going to consolidate. You're going to combine them. And finally, you're going to tell what is the answer to that question. So this is what we are doing. Taking the opinion of all our friends, combining them, and finally giving the answer to our final question. So when you talk to your friends, when you consult them, the chance of answering the question is very high. So therefore, the chance of winning $1 million is also very high. So this is what we have to understand. That is the reason why you are using the concept of your Ensemble models. So this is the background what you're supposed to have when you are discussing our Ensemble model concept. Now, we have to understand some terms here. What are those terms is? We have something called as allocation function. We have a term called allocation function first. So what is the allocation function going to do? It is going to dictate how much of training data each model is going to receive. So how much data can be shared with each of your model is going to be decided by your allocation function. So allocation function is going to decide whether model 1 is going to receive the entire data set or not. Allocation function is going to decide what percentage of data you have to supply to your model. Allocation function is going to decide what percentage of data you have to supply to model. So what is happening? You are ensuring that not every model is receiving 100% of the data. You are ensuring that not every model is receiving 100% of the data. That is what you're ensuring. So now when every model is not receiving 100% of your data, then there is no scope for over learning from your data set. Yesterday we have seen this concept. So there is no scope for over learning from your data set. Now when there is no scope for over learning from your data set, what can you call those machine learning models? They are going to be called as weak machine learning models, because they are not in a position to learn everything from the data set. They are not in a position to learn from all the features that you have in your data set. That is the reason why you can call those machine learning models as weak machine learning models. They are weak learners. Model 1 is a weak learner because you are not supplying all the information. Model 2 is a weak learner because you are not supplying all the information. So that is the reason why we were calling these machine learning models as homogeneous weak learners. That is the reason why we were calling these machine learning models as homogeneous weak learners. So now, after you have considered your homogeneous weak machine learning models, you can use them to understand your data, make predictions. So they are going to make predictions. P1, P2, P3. They are going to make predictions. P1, P2, P3. Now, what is our job? Our job is to combine all these predictions. So our job is to consolidate all these predictions. So how can you consolidate all these predictions? A simple method could be take the average. Take the average of 3 predictions and you can decide what is going to be your final prediction for your ensemble model. Or what you can do, you can take a majority votes. What do you mean by majority vote? So P1 has predicted 1, P2 has predicted 1, P3 has predicted 2. So based on the majority of votes, your final prediction can be 1. So you can either use the concept of majority votes, or you can use the concept of taking the average of the predictions made by your machine learning models, and then you can decide what is going to be your final prediction. So any of these methods you can use. These are just options what we have, and you can use them to understand what kind of predictions your ensemble model is making on your data set. So this is the background concept of your ensemble techniques, ensemble models. This is the understanding what all of us are supposed to have. Now, so in the last class, we were discussing the concept of decision trees first. Now, in today's discussion, we are going to see the concept of bagging. So what is the full form of bagging? Bagging is called as bootstrap aggregating concept first. Bootstrap aggregating or bagging. It is an ensemble algorithm which is going to combine predictions. Which is going to combine predictions from multiple decision trees using a majority voting mechanism. Using the concept of majority votes. This is the definition of bagging. This is the definition of bagging. Under bagging, what is the example that we are going to discuss? We are going to study the concept of a random forest first. We are going to study the concept of a random forest. So random forest is a bagging based algorithm for us, where only a subset of features are selected. So what we are going to do, we are only going to supply a subset of features to each and every machine learning model. And using only these subset of features, your machine learning models are going to learn from this data and make their predictions. And we are going to combine all these predictions together. And you can call such kind of model as a random forest. So forest is nothing but it is a collection of trees. So collection of decision trees, you can call it as a random forest for us. Why it is random? Because randomly we are going to supply the information to each and every decision tree. So this is the example what we are going to discuss under the concept of bagging for us. Then boosting we are going to see. So boosting is nothing but where models are built sequentially. So sequentially, every machine learning model is connected, which will try and minimize the errors which are caused by our previous models, and thereby increasing the performance of your model. This is called as boosting. So boosting, what is the type of boosting that we are going to study? Add a boost. Or you can call it as adaptive boosting. Adaptive boosting method. And then we have different other boosting methods also we have gradient boosting methods. So gradient boosting methods, they work on the concept called as gradient descent algorithm. So this is a very famous algorithm, gradient descent, which will help us minimize the errors, especially in case of your sequential models. So what are the different boosting techniques which are based on your gradient descent algorithm? You have one boosting technique called as XGBoost. This is called as extreme gradient boosting. And then you have another boosting technique which is also based on your gradient descent architecture. It is called as LGBM, light gradient boosting method. It is called as light gradient boosting method, or LGBM you can call. So these are the other boosting methods which are available for us, which are based on the concept of your gradient descent architecture. Now, with this understanding, let us try to discuss our first ensemble technique, which is called as bagging for us. So bagging we are going to discuss. So bagging is one of the first ensemble methods to gain widespread acceptance for us. It is one of the first ensemble methods which was developed. And the full form of bagging is called as bootstrap aggregating for us. So we have to understand what is this concept, bootstrap aggregating. In few minutes, you are going to see what is this bootstrap aggregating. So what is the bagging concept? How does it work? Bagging generates a number of training samples by bootstrap sampling the original training data set. So it is going to generate training data sets by bootstrap sampling the original training data. So we are going to see what is this with the help of one example. And once we have created these smaller training data sets, then these data sets are then used to generate a set of models using our machine learning algorithm. So we are going to apply our machine learning models on these smaller data sets, what we have bootstrap sampled from our original training data. Then once your models have been developed, you can use those models and make your predictions. So model predictions are going to be made, and we should be in a position to combine all the predictions. So how can you combine all the predictions? Either you can use your voting concept, majority votes, or we can use our averaging concept. So anything we can use depending upon what kind of problem we are trying to solve. If you are trying to solve a classification problem, then you can use the concept of your majority voting. And then if you're trying to solve your numerical prediction problem or a regression problem, then you can work with your averaging method. So any method you can use depending upon the problem, what you're trying to solve. So this is the background of our bagging. Now, let us try to understand how this bootstrap sampling procedure is going to work. So what do you mean by bootstrap sampling procedure? So bootstrap is a powerful statistical method which is used for estimating a quantity from sample data. So let us try to understand this with the help of an example. Suppose you have 100 observations in your data. Suppose you have 100 observations in your data and you want to find out the average of these 100 observations. How are you going to find out the average? Add all your observations, x1 plus x2 plus x3 plus x4 plus so on x100 divided by 100. This is going to be the average of all our observations. This is going to be the sample mean for our data set. So take the summation of all the elements what you have in your data set divided by 100. This is your sample mean. Now, what is the problem with this sample mean calculation is because our sample set is very small. Because our sample set is very small, therefore, our computation of mean can always have error. Because our sample set is very small, the computation of mean can have error. So how can you improve the estimate of our mean? How can you improve the estimate of our mean calculation on our sample data set? So what is that we are going to do is, we are going to create subsamples. So you can create as many subsamples or subsets from our data set. And then you can find out the mean for each and every subsample. So imagine you have created subsample 1, subsample 2, subsample 3, subsample 4. And so on, you have created 100 subsamples from your original training data set. So now what you are going to do, you are going to apply mean. You're going to find out the mean for every single subsample what you have created. Find out the mean for every single subsample what we have created. This is what you're going to do. Now, after finding out the mean for every single subsample, then take the average of all these means. Take the average of all these means. M1 plus M2 plus M3 plus so on M100 divided by 100. So take the average of all the means, and this is going to be the final estimate for our sample mean. This is going to be the final estimate for our sample mean. So this method, what we have applied is called as bootstrap method. So create as many subsamples as you want, find out the mean for each and every subsample, and then take the average of all the means. Calculate the average of all the collected means. And that average value is going to be considered as the estimate for sample mean for our data set. So this procedure will be followed by our bagging ensemble technique. Now, how can we apply this logic in our machine learning example? So let us consider your data set is having 1,000 observations. Let us consider our data set is having 1,000 observations. Now you have decided to use C 5.0 algorithm. So we have decided to use C 5.0 algorithm. This is what we are doing. Now, what is the first step we are going to do? Create as many subsamples as you want from our data set. Subsample 1, subsample 2, subsample 3, subsample 4. We have created some 100 subsamples like this. As many you want, 500, 1,000, as many as you want, you can create your subsamples. Now you are going to build your C 5.0 model on all these subsamples. You are going to build your C 5.0 algorithm on all these subsamples. So train your C 5.0 model on each of your samples. Then, once you train your model, make your predictions. These are my predictions. P1, P2, P3, and so on, P100. I'm going to get 100 predictions I'm going to get because I have created 100 subsamples. Now what you're going to do, take the average of all these predictions. Take the average of all these predictions and you can call this as your final prediction for your bagging ensemble model. So here we are using the concept of bootstrap sample. That is what we are using. We are creating our subsamples. Now suppose if we have bagged 5 decision trees, that means if our bagging ensemble model is having 5 decision trees. Now, our first decision tree has predicted blue. Our second decision tree has predicted blue. Third decision tree has predicted red. Fourth decision tree has predicted blue. Fifth decision tree has predicted red. Then what is your final prediction or classification? Blue has been predicted 3 times. So most frequently, our blue category has been predicted by our bagging ensemble model. So what is your final prediction going to be? My final prediction is going to be blue for my target variable because this is the category which has been frequently predicted by my bagging ensemble model. This is what we have to understand. This is how the model is going to work. So this is a simple example what we have discussed. Now, some points to remember. Some points to remember first. When bagging with decision trees, we are less concerned about individual trees overfitting the model. We are less concerned with individual trees overfitting our model or overlearning from our model. Why are we less concerned? Because we are ensuring that not every model is going to receive 100% of your data. Not every model is going to receive all our features. So this is what we have to keep in mind. So because they are not going to receive the entire training data, because they are not going to receive all the features, what is the advantage? There is no question of model over learning from your data. There is no question of individual decision trees overfitting on your data set. So for this reason, what is that you can do? You can allow the individual decision tree to grow very deep. So you don't have to worry about pruning your decision tree. You can allow your decision tree to grow very deep because there is no question of overfitting your decision tree on your data set. So you don't have to worry about pruning because you are dealing with weak machine learning models here. So bagging concept makes use of weak machine learning models. So when you're applying your bagging ensemble technique, we don't have to worry about pruning your individual decision trees because there is no question of those decision trees overfitting on your data set. So these decision trees are going to have high variance and low bias. So you can allow your decision trees to grow very deep. You can expect the decision tree is going to have high variance and low bias for us. So these are important characteristics of your submodels when you're combining your predictions using your bagging concept. So these are some points to remember, some important characteristics of your submodels when you're trying to make your predictions using the concept of bagging first. So keep all these concepts at the back of your mind. They are important for us. Now, so what are the parameters that we have to consider when bagging your decision trees? Number of samples and the number of decision trees that you want to consider. So you can try and increase the number of decision trees. So what you can do is, you can try and increase the number of decision trees and you can find out whether the accuracy for your model is increasing or not. So you can try and increase the number of decision trees. You can build a bigger ensemble model and see if you are able to improve the accuracy for your model or not. But you have to be careful that when you have larger number of individual models, you may take more time for building your model. But you can ensure that it is not going to overfit your training data set because we are dealing with weak machine learning models. This is what we are dealing with. Weak machine learning models. So this is the background, what you are supposed to have at the back of your mind before you apply the concept of your bagging ensemble technique. It is very important for us. So now, what is the application that we are going to discuss? One application of your bagging ensemble technique is random forest. So random forest is an application of your bagging ensemble model. This is the application of your bagging ensemble technique. Now, so random forest, like we know, it is made up of many decision trees. It is a collection of trees. Now, what are the two important concepts which can help us understand why it is called as a random forest? Why do we have this randomness here? The two reasons are because random sampling of training data will be used for building your models. So random sample data will be used. That is one reason why it is called as random forest first. And then random subsets of features will be considered for building your models. So one is random sampling of data will be used. That is one reason. And also a random subset of features will be considered for building your models. So these are the reasons why you can call this bagging ensemble technique as a random forest class. That is the reason why you can call them. So when you're building your models, each decision tree is going to learn from random sample of data. So you can understand that because this is a bagging ensemble technique, obviously the samples will be created using our bootstrap sampling method. So samples what you are going to create will be done on the basis of your bootstrap sampling procedure. Same procedure we are going to use. Now, when we are supplying the features to our machine learning models, you are only going to supply a subset of features. You are not going to supply all the features. Suppose if you are working with 16 features, then there is an approximation what you can make on deciding how many features you can supply to each of your machine learning models. So you can approximate to square root of 16 features. And you can decide that 4 features have to be supplied to each and every decision tree model. So this is a small approximation, what you can remember. That if you are working with n features, then square root of n features can be used for building your each and every decision tree model. So if you are working with 9 features, then what is the approximation? You can approximately have 9 features in total, and then you can decide to supply only 3 random features to each and every machine learning model in our random forest ensemble technique. So this is how you can decide subset of features. So out of 16 features, I'm sending only 4 features. Out of 9 features, I'm only sending 3 features. So not all the features I'm supplying to my machine learning model. So this is the reason why we have called them as weak machine learning models, because we are not giving them a chance to learn from all the 16 features. We are not giving them an opportunity to learn from all the 16 features or to learn from all the 9 features. So imagine that these are the machine learning models what we have developed. So how many machine learning models you have? How many decision tree models? 1, 2, 3, 4, 5, 6, 7, 8, 9. Totally 9 machine learning models you have developed. So it is a random forest with 9 decision trees. Now, what will be your final prediction for this random forest? What will be the final prediction for this random forest? So because 6 of your decision trees are predicting 1. So using the majority voting concept, what is it you can say? You can say that the final classification for my random forest is going to be 1. Because 1 is frequently predicted by my individual decision tree models. 6 of my decision tree models are predicting 1. So this is how I can make use of my random forest and improve the robustness, reliability of my model. And also I can use it to improve the accuracy for my machine learning model. So now my question is, why do you see decision trees predicting different values? Some decision trees are predicting 1, some decision trees are predicting 0. What is the reason for this? Why decision trees are predicting different values? 1, 0. Because not every decision tree is being supplied all the information. Not every decision tree is being supplied all the features. So because I'm supplying randomly my subset of features, because I'm randomly supplying my data to all my decision trees, So you can expect that decision trees are going to come up with different predictions. So that is the reason why you have different decision trees making your prediction 1 and 0 also. So the fundamental concept behind random forest is simple, but it is a powerful. Large number of relatively uncorrelated models operating as a committee will always outperform any individual constituent models. So a large number of relatively uncorrelated models operating as a committee, this is our committee, will definitely outperform any of your individual constituent models. So this is the concept of the random forest first. So this is how you are going to build your random forest. So now the question is, if you randomly supply your features, what is the concept that you are going to use for deciding which feature should be considered as a root node? So how is my each and every decision tree going to decide among these 4 features to be my most important feature? How is my decision tree going to find out? So that concept we are going to discuss after the break. So take a break here for 10 minutes and come back after the break. We are going to discuss the remaining topics. So let us continue our discussion. So the question what we were asking was, how is our decision tree going to select what should be the root node if I supply 4 features or if I supply 3 features? What is the concept that we have discussed yesterday? If you are using your C 5.0 algorithm, then how is C 5.0 algorithm decide what should be the root node? It is going to use the concept of entropy and information gain. So whichever feature is capable of reducing my entropy by maximum extent, that feature is going to be considered as our root node. If you are working with your CART algorithm, then what is the logic? How does this algorithm select the root node? It will use the concept of Gini impurity. So whichever feature is capable of reducing the Gini impurity by maximum extent, that is going to be selected as the most important feature. So the same logic will also be applied in our random forest ensemble technique also. Same forest, same algorithm, and same concept will be applied. It is the concept of entropy and information gain, or it is the concept of your Gini impurity. So now, how can I write the pseudocode? How can I develop the logic for my random forest? So what is the first thing? There are a couple of points here. We have 5 points. Let us try to understand what these 5 points are. So first you are going to select K features from a total of M features. You have to ensure that K is very, very less than M. So if M is 16, you can select K is equal to 4. If M is 9, you can select K is equal to 3. The bottom line is you have to ensure that K is very, very small than M. So this is what we have to ensure. Among the K features, how are you going to decide what is the best split point? It is going to use the concept of entropy and information gain, or it is going to use the concept of Gini impurity. So imagine this is my best feature. And now what I'm going to do, I'm going to split my node into daughter nodes. So I'm going to split it into daughter nodes. These are called as daughter nodes for us. Then what I'm going to do, I'm going to repeat my process 1 to 3 until L number of nodes have been reached. What is this L number of nodes? Suppose if I define L as 7. Now how many nodes I have? In total 1, 2, 3, 4, 5, 6, 7. So until I create these 7 nodes, I'm going to keep splitting my nodes into daughter nodes. That is what I'm going to do. So I can define how many nodes I want to create for my decision tree. And then what does that I have to decide? What should be my forest size? I have to decide. That means how many decision trees I am supposed to consider for building my forest. So if I consider 2 decision trees for building my forest, then I have to repeat this process for my second decision tree also. If I think I'm going to create a forest of 3 decision trees, I have to repeat this method for my third decision tree also. So build a forest by repeating steps 1 to 4 for n number of times, because you want to create n number of trees. N can be any number for us, 5, 10, 50, 100, 500, 1000. So as many decision trees as you want. You are going to repeat this logic and you are going to build your random forest. That will be the size of your forest. It will have those many decision tree models. Now, what are the advantages of random forest algorithm? The advantages of random forest algorithm is it can be used for both classification and also regression problems. You can use your random forest for solving your classification and also regression problems. Random forest classifier will be able to handle your missing values. Even if information related to one particular attribute is not available, it is going to look for other piece of information which is available for us, and it is going to use that attribute and build your decision tree. So random forest classifier is capable of handling your missing values. Overfitting problem will never come because random forest algorithm is going to deal with your weak machine learning models. It is going to deal with weak machine learning models first. And then random forest algorithm can also be used for feature engineering. It will help us identify what are our important features. It is going to help us identify what are our important features. So many advantages you have for your random forest model. So let us continue with our discussion of next ensemble technique, which is boosting. So far we've been discussing bagging. Now it is time for boosting for us. So what is your boosting ensemble technique? Boosting ensemble technique, it attempts to create a strong classifier from a number of weak classifiers. So it is the same concept. You will be working with a bunch of weak machine learning models. But how are you going to construct your ensemble? So you are going to build a model from your training data set. And then you're going to create a second model that will attempt to correct the errors from your first model. So every machine learning model will be sequentially connected. And it is going to help us attempt and rectify the errors what the previous model has produced. So models can be added in a sequential manner until the training set is predicted perfectly. So you can keep on adding your models in a sequential manner for us. So AdaBoost is the first boosting technique which was successfully developed for a binary classification problem. So adaptive boosting technique was one of the first boosting algorithms to be created for a binary classification problem. And later on, they extended the concept to solve a multi-class classification problem also for us. So it is the best starting point to understand the concept of boosting first. So AdaBoost can be used to boost the performance of any machine learning model. So I can apply my AdaBoost classifier on top of my decision tree model, and I can boost the performance of my decision tree model. So that is what we are going to see. It is best used with weak learners. So you can use your AdaBoost model with your decision tree model, and you can see what kind of results it is going to give. Now, so let us try to discuss the concept of your adaptive boosting or AdaBoost. So imagine this is your training data set that we are working with. And now you have a bunch of negative observations and you have a bunch of positive observations as they're here. So what is the first step that you can do? You can partition your data or split your data. We can split our data set. So now when I make my first split, that is when I do my first iteration, when I build my model on my data set, my model is not able to correctly classify all my observations. Some negative observations, it is misclassifying them as positive. That is why you see them in the positive region. And it is also misclassifying some positive observations as negative observations. So there is some classification error. So this is what we can discover from the first iteration. So how does your model work is, initially, all your observations, suppose you have n observations in your data set. Suppose if you are working with n observations, every observation will be given a weight of 1 by n. That means every observation will be given equal weights. That is the starting point for us. Then after the first iteration, some of these observations will be misclassified, right? So those misclassified observations are going to receive higher weights. So the model focuses on assigning more weights to observations which are misclassified for us. That is the focus. So now the second model what you develop is going to understand that these are the observations which are misclassified and therefore they have been assigned more weights. So it will take into consideration these new larger weights and will try to correctly classify our misclassified observation. That is what it is going to do. So this is the background logic, what your AdaBoost algorithm is going to use. Now, what is the mathematics behind your AdaBoost algorithm? At every iteration, after you build your machine learning model, you are going to compute something called a stage weight. So these are all technical terms. You are going to compute something called a stage weight. How are you going to compute your stage weight? What is the formula? This formula you are going to use. So if you look at this formula, natural logarithm of 1 minus error by error is having something called an error. So first, we have to find out what is the misclassification error, which is caused by our machine learning model. Then using that misclassification error, we have to substitute that in this formula and you have to find out something called a stage. And then using stage weight, we are supposed to update our weights. We are supposed to update our weights for our misclassified observations. So that is the concept. So initially, you are going to start with 1 by n observations for us. So keep this concept at the back of your mind, and we are going to discuss some examples. How is it going to work? Now, this is our original data. And then we have built our model. So our model is developed. Now, after we develop our model, we can understand that our negative observations are being misclassified as positive. And one of our positive observations is also being misclassified as a negative for us. So therefore, what is that you're going to do? Before building your next model, you have to update your weights. So weights for all your misclassified observations are going to be updated first. And then in the next iteration, your new model is going to take into account all these updated weights and it will try to rectify all the misclassified observations. So now if you see, it is clearly trying to separate out your negative observations from your positive region. So it is clearly trying to separate out my negative observations from my positive observations. That is the advantage. So samples which are incorrectly classified in one iteration receives more weights in the next iteration. So they are going to receive more weights. What about samples which are correctly classified in the first iteration? They are going to receive same weights. So my observations which are correctly classified in my first iteration are going to receive the same weights. Only observations which are wrongly classified are going to receive more weights for us. This is the point what you have to keep in mind. So that is what you are supposed to understand. Now, so each sample, what is the starting point? We are going to start off with equal weights. We are going to start off with weights 1 by n, and then you are going to fit your first machine learning model with your initial weights. And after the fitting of your model, find out what is the misclassification error. Then compute your stage weight. I told you we have to compute your stage weight. What is the formula? This is the formula, log of 1 minus error by error. Find out what is your stage weight. And then you are going to update your weights. So we are going to discuss what is the formula for updation of weights in few minutes. So from your old weight, you have to update your weights for all those observations which have been misclassified for us. So that is what you have to do. Updation of your weights. Now, let us discuss with the help of one example. Error is nothing but it is the misclassification rate. So our job is to correct the number of observations which have been misclassified by models. So for example, if your model has predicted 78 of the 100 observations correctly, if your model has predicted out of 100, 78 observations correctly, then what is the error rate? 0.22. So this is the error rate or misclassification error. What is the formula? 78 minus 100 divided by 100. You are going to get your error. Now, let us consider one example. So we have our observations, actual value, predicted error. So we have our observations 1, 2, 3, 4. 4 observations you have. And then actual value is 1, predicted value is 0. Actual value is 1, predicted value is 1. Actual value is 0, predicted value is 0. Actual value is 1, predicted value is 1. Imagine this is how your model has predicted for us. Now, if you look at your first observation, actual value is 1, predicted value is 0. So what is the error? 1 minus 0, it is 1 for us. Actual value is 1, predicted value is 1. What is the error? 0. Actual value is 0, predicted value is 0, 0. Actual value is 1, predicted value is 1, predicted error is 0. So this is the model performance. So before we proceed forward, it is that time of the day where attendance sheet is being circulated in your chat window. So fill in your details without making any mistakes and come back to our session. You can come back and we can continue our discussion. So please try to fill in all your details in the attendance sheet. Now, so this is our data. This is our model performance. So now what we have to understand, initially, we are going to assign weights equal to 1 by n. So what is our n? N is 4 because we have 4 observations. So initially you are going to assign 0.25 as weights for all your observations. So these are my initial weights. Now, after the first iteration, what is happening? Your observation 1 has been misclassified for us. So how are you going to update the weights? You are going to update the weights first by calculating the error. You have to first find out what is the misclassification error for my model. So error is equal to, what is the formula? Sigma I is equal to 1 to n wi into predicted error divided by weights. So this is just nothing but you are trying to compute your weighted average of your errors. So now what is wi? It is 0.25 into predicted error is 1 plus 0.25 into 0 plus 0.25 into 0 plus 0.25 into 0. So weights into predicted errors divided by total summation of weights, which is 1. So misclassification error is 0.25. So after the first iteration, this is the error. What you have calculated after the first iteration. Now, what is that we are supposed to do? We are supposed to find out what is our stage weight. We are supposed to find out what is our stage weight. So what is the formula for stage weight? Log of 1 minus error. What is the error that we got? 0.25. So substitute your error 0.25 in this formula. Find out what is your stage weight. Now, second step is also done for us. After finding out the stage weight, how are we going to update our weights? So we have now a new formula. W new is equal to W old minus, or not minus, into e power stage into predicted error. What is the formula? W new is equal to W old into e power stage into predicted error. So find out what is the stage weight from the second step. Substitute it here. And what is the predicted error? Predicted error is 1. So W new is equal to W old into e power stage into 1. So now you can clearly understand that when you are multiplying your old weight with e power something, you can expect the new weight to be clearly more than our old weight. Because mathematically, when you are multiplying something with e power some value, you can expect that the new weight is going to be more than your old weight. So that is how you can clearly update. You can increase the weight for your misclassified observations. You can do that. So this is the method what we are going to use. So for the first observation, initially we have assigned it as 0.25. Now W new weight is going to be 0.25 into e power stage weight. So clearly, when you are multiplying with e power something, your W new weight is going to be more than 0.25 for us. That is what you are going to do. Now, what about all the observations which have been correctly classified? Suppose, second observation you take. Second observation has been correctly classified for us. So W old into e power stage weight into what is the predicted error? It is 0. So e power 0 is 1. So W new weight is going to be equal to W old weight. So all the observations which are correctly classified, they will have no updation in weights. They will have no updation in weights. They will remain as it is. Their weights will not change for us. So this is the concept what you have to remember. So this is how your mathematical calculations are going to happen in the background when you are applying the concept of your AdaBoost classifier. So in Python, ready-made functions are there and you can use them and boost the performance of your machine learning model. Now, what is the next ensemble technique? It is called as stacking ensemble technique. So stacking ensemble technique is going to work on the logic of heterogeneous learners. Heterogeneous learners. So no longer we'll be working with our homogeneous machine learning models, but time has come for us to work with our heterogeneous learning models. So stacking is a concept where you are going to build multiple models. So on your input data, you are going to build multiple models. Multiple classification models I can build. Logistic regression. This can be one model. Support vector machine. It can be another model for us. And I can build my decision tree. And now there will be predictions that you have to control. So every model is going to make some prediction. Logistic regression is going to make a prediction. Support vector machine is going to make a prediction. Decision tree is going to make a prediction. So how are you going to control all these predictions? How are you going to control? How are you going to combine all these predictions? That is the question. So we are going to use a supervisor model. What is a supervisor model? It is simple example is a voting ensemble model. You can use a voting ensemble model. If my logistic regression has predicted 1, if my support vector machine has predicted 1, if my decision tree has predicted 2, so based on my voting ensemble model, which prediction value has received more weights? 1. So therefore, your final prediction is going to be 1 for your stacking ensemble model. That is the idea. So we are going to work with our supervisor model. You can take the help of your voting ensemble model and you can make your predictions for your stacking ensemble technique. So the supervisor model is going to learn how best it is to combine the predictions for our primary models, logistic regression, support vector machine, and decision tree for us. So not only you can do this, but also you can create an ensemble of ensembles. That means instead of having my decision tree model here, I can have my random forest model. So now what am I doing? I'm creating an ensemble of ensembles. So random forest is already an ensemble model. So now you're trying to create an ensemble of ensembles. So this can also be created and you can apply this ensemble of ensemble models to make your predictions. You can do this to boost the performance of your model. You can create such kind of ensemble of ensembles and you can make your classifications, make your predictions. You can do it. So this is the idea about our ensemble techniques, ensemble models. Now, how can you apply these concepts? Let us try to understand. Let us discuss our concept. So first we are going to focus on our bagging ensemble technique. Now from pandas, import our read underscore CSV function for reading our CSV files. Then from ExcelR.model underscore selection, import k-fold cross validation. So k-fold cross validation we are doing for creating our subsamples. Remember, bagging classifier is going to work on subsamples. So we are doing that for creating our subsamples. And from ExcelR.model underscore selection, import cross validation score. So cross validation score is a function what we are using to find out the accuracy on each of our subsamples. That is the function what you are going to use. And then from ExcelR.ensemble, we are saying import bagging classifier. So this is the function what you have to remember. So all these libraries you have to remember, all these functions you have to remember. Then only you will be in a position to apply our concepts. And from ExcelR.tree, import decision tree classifier. This we have seen in our decision tree model. So this we have seen. So what is the file name? I'm going to use a Indian diabetes dataset. This is a very famous, popular dataset that we are going to work with. And you have different features in this dataset. You have pregnancy, plasma, pressure, skin, test, mass, pedigree, age. All these are our independent variables. And you have to predict whether that person is going to get diabetes or not. 1, if that person is going to get diabetes. 0, if that person is not going to get diabetes first. So this is our model, what we are going to develop. So now read your file name and include these names as your column names in your data set, and then divide it into X and Y. So X is going to have all your independent variables, and Y is going to have your target variable. So what is that we are saying? Apply my k-fold. How many subsamples I want to create? 10 subsamples I want to create. And then I'm going to initialize my decision tree classifier model. And I'm saying how many trees I want. I want to create 100 trees. This is the size of my forest that I want to create. So bagging classifier with 100 trees. Now you're going to build your model. You're saying bagging classifier and include my decision tree classification model. And how many decision tree classification models I want to use? I want to use 100. 100 trees I want to use. And once your model is ready, you simply apply the model on your X and Y data. Find out the accuracy on each and every subsample. Find out the accuracy on each and every subsample is what we are going to do. And then take the mean. Take the mean of all the accuracies. How many subsamples you have created? 10. S1, S2, S3, S4, S5, S6, S7, S8, S9, S10. Take the accuracies of all your subsamples and then find out what is the mean accuracy. This is what you are going to do. So this is the mean accuracy for my model. So this is how I can develop my bagging classification technique. This is what I'm going to do. Now, next, I'm going to build my random forest classification model. I'm going to do this. Now, from pandas, import read underscore CSV. And from ExcelR.model underscore selection, import k-fold cross validation for creating your subsamples. And then from ExcelR.model underscore selection, import cross validation score. So all these things are same, just like how we have defined in case of your bagging classification. And from ExcelR.Ensemble, import your random forest classifier. This is a new function what we are using because we are going to build our random forest classifier or random forest classification model. That is what we are going to do. Now, divide your data into X and Y. This is what we have. And how many trees I want? 100 trees I want to use, 100 decision trees. And then, because only I have to supply my subset of features. So total I have 9 features and I can approximate square root of 9. 3 features to be supplied to our decision tree models. So 3 features will be supplied to each and every decision tree. And it is going to make your prediction using these 3 features. That is what we are telling. Now, apply your k-fold. I want to create 10 subsamples. And now build your model. So apply my random forest classifier. And what should be my forest size? My forest size is 100. And then how many features are going to be supplied for each and every decision tree? 3 features. And find out what is the accuracy now on your X and Y data. So all your subsamples, you are going to find out your accuracy. S1, S2, S3, S4, and so on, S10. And now take the mean of all the accuracies. Take the mean. So this is the mean accuracy that I'm getting for my random forest model. So this is how I can build my random forest classification model. Now, add a boost classification model. So from pandas, import your read underscore CSV function to read your file from ExcelR.model underscore selection, import your k-fold cross validation. And from ExcelR.model underscore selection, import cross validation score for finding out the accuracies. So this is what we have. Now, from ExcelR.Ensemble, import your add a boost classifier. So this is the function what we are going to use. Add a boost classifier first. So ready-made functions are there. So all the heavy lifting, all the mathematical calculations what we have seen, it will be taken care of by our add a boost classifier. So that is the benefit what we have. Now this is the file name, Indian diabetes. So read the file name with all the required column names for us and divide your data set into X and Y. Now, X is going to have all your 8 independent variables. Y is going to have your target variable for us. So how many trees I'm saying? 10 trees. So use my 10 trees. And then how many subsamples? I'm saying create 10 subsamples for us. And now I'm going to apply my add a boost classifier with 10 trees. I'm applying my add a boost classifier, add a boost ensemble technique with 10 trees. And then find out the accuracy on your X and Y data on all your subsamples. So this is what you're doing. Now take the mean of your accuracy. What is the accuracy that you're getting? 75.25% is the accuracy for my model. So in all these examples, what we have discussed, you can increase the number of trees. You can increase the number of trees and you can experiment with this program and see if you are able to improve the accuracy for your model. So you can do that. You can see if you are able to improve the accuracy for our model or not. You can try that out. Now, finally, we have our stacking ensemble model. So what is our stacking ensemble model? Telling us from pandas import read underscore CSV for reading your file. From ExcelR model underscore selection, import k-fold cross validation. From ExcelR model underscore selection, import cross validation score for finding out the accuracy. And now we have our heterogeneous models. So from ExcelR linear underscore model, import logistic regression. From ExcelR tree, import decision tree classifier. So all these functions you have to remember. From which library you have to import those functions, you have to remember. And from ExcelR support vector machine, import your support vector classifier, SVC. Support vector classifier first. Now, I told you there will be a supervisor model. So what is the supervisor model that we are using here? We are using our voting classification. Voting ensemble we are using. So from ExcelR.ensemble, import your voting classifier. So read your file. This is the name of your data set, and these are your column names that you have. And divide your data set into X and Y. And these are the 10 subsamples what I want to create on my data. And now I'm creating my submodels. So submodels are going to be my logistic regression, and then decision tree and support vector classification model. So create all your model 1 is logistic regression. Model 2 is nothing but your decision tree classifier. And then model 3 is nothing but your support vector machine. So you can also provide names like this. First model is called as logistic. Second model is called as cart. Third model is called as SVM. So you have 3 models, and now all these are going to act like your submodels, or you can call them as estimators here. You're creating an empty list where you can create all these submodels. Now, once you are through with that, we are going to create our ensemble, our supervisor model. This is our voting ensemble supervisor, which is going to act upon all our estimators. And then now, everything is ready. Our submodels are ready. Our estimator model is also ready. So now, take your ensemble and then apply it on your X and Y and find out what is the accuracy what you are getting. And then take the mean accuracy. So this is how you can develop your stacking ensemble model. So here I can use different heterogeneous models. So I can use any classification model. My logistic regression, support vector machine, decision tree. I can use my random forest. I can use my KNN algorithm. I can use my naive algorithm. So all these things you can use. And you can create a stack of all these models. And you can have a supervisor model, like a voting classifier. And you can make your predictions or classifications on your data set. So this is the idea of our concept, ensemble models. So it is a very interesting technique for us. Ensemble methods. So remember all these concepts, whatever we have seen so far. Your bagging classifier, followed by what is the example that we have discussed in our bagging classifier? A random forest. So why is it called random? We have to remember those points. And then next we have discussed our boosting ensemble technique. So under boosting ensemble technique, what is the example that we have seen? Add a boost. So try to remember those technical terms what we have discussed. Initially, you're going to start off with equal weights. Then you're going to calculate your classification error. After calculating your classification error, find out your stage weight. Remember the formula. And then after calculating your stage weight, you are going to update your weights. So W new is equal to W old into E power stage into predicted error. So these are the formulas what we have discussed. So all this heavy lifting will be taken care of by your AdaBoost classifier in Python. So simply we have used AdaBoost classifier and we have decided how many trees you want, 10 trees. And try to increase this number of trees. Try to change this from 100 to 500. Check if you are able to improve the accuracy for your model or not. So we are free to experiment with the program that we are discussing. So that is the idea what you're supposed to have. And then we have discussed our stacking ensemble model. So stacking ensemble model is the model which makes use of heterogeneous submodels. So we have worked with logistic regression. We have worked with a support vector machine. And we have worked with our decision tree models. And then you have to also decide what should be your supervisor model. So we have worked with our voting ensemble. So decide what should be your supervisor model and simply apply this on your data set. And you can make your predictions for your stacking ensemble data. So ensemble models are used predominantly to improve the reliability of our machine learning model, to improve the robustness of our machine learning model, and then to also improve the accuracy of our machine learning model. So this is the reason why we can work with our ensemble models. So this is the concept for our today's discussion. So again, tomorrow we are going to connect with another topic under our supervised machine learning concepts, and we'll continue our journey in data science and other related topics. So till then, take care. Thanks for your time, and I'll see you all again tomorrow.